And today we'll talk about sequences and summations. Sequences are basically very important to in computer science mathematics because they frequently occur in many scenarios. Sequences are basically ordered list of elements. For example, 1, 2, 3, 5, 8. This is an order of this is a list of ordered elements. They are it might seem that there is no pattern to them, but still they are in order. Again, we have 1, 3, 9, 27, 81. Now, this is a very familiar pattern. It is basically 3 raised to power n. So, 3 raised to power 0 is 1, 3 raised to power 1 is 1, 3, 3 raised to power 2 is 9, 3 raised to power 3 is 27, and then so on and so forth. So, let's look at some of the terminologies and how we can represent a sequence. It might come out as a surprise, but a sequence is essentially a function and it is a function from a set of integers. For example, the sets 0, 1, 2, 3, 4, and it goes up to any number of terms you want. And it's again, it can also start from 1, 2, 3, 4 to a set S. Now, as you can see that we have in this case, the function has a domain of which is a subset of integers. So basically, we are talking about integers which are from 0 to n or from 1 to n. And as you would just see in a while that why sometimes we have 0 included and sometimes we don't have 0 included. But the set S can be anything. It could be set of students, it could be set of faculty members, it could be anything. So for example, in this case, the set S, it could be the list of students and we could say, okay, who is the first student, the top at the top of the class and we map it to a student. Who is the second student? We map it to another student and 3 and 4. And the sequence would be a sequence of students in the order of their ranking in the class. So in the case of sequences, we have notations, for example, an, which is used to denote the image of the integer. So as you know that any function has two parts, the domain and the image. So here, so the domain and the image, in this case, the image is the set S. So the image would be an. So we can think of an as the equivalent of the fn, which is a function from the 0, 1 to 3 to up to s to any number to s. So we call an a term of the sequence. So an is the term of the sequence. So for example, look at the sequence an. Now an is a term and this is a set. So the set of this sequence, the sequence is also a set of numbers. So an is given by a formula 1 over n. Now here, if we start with n is equal to 0, as you can see that it would be a failure, a huge failure, because 1 over n, 1 over 0 is not defined at all. So what is the first number? an. an would be 1, 1 over 1, a2, 2. You replace n by 2 here and you get 1 over 2, then a3, a4, and so on and so forth. So this is a sequence which it's a good example of a sequence where we have understood why sometimes we don't start with n is equal to 0 and how a sequence can be represented by a equation. And earlier example that I gave you about the students, it could be any arbitrary set. Now, something important is a geometric progression. So it is geometric progression is a sequence, which means again it is again a set, but sorry, it's again a function. So a geometric progression is a sequence which is a function from subset of integers to some set. Now that set is defined by this formula, this progression. So the initial term would be a and the common ratio would be r. So the common ratio r, so the initial term a and the common ratio r are real numbers. Now for example, if you start with a is equal to 1 and r is equal to minus 1, so what we do is we start from 0. So this first term you should be very very clear that it is not equal to a, it is actually equal to a into r raised to power 0. So you can see that it starts from 0 1, 2, and to n, and it can go on wherever you want it to go. So in this case, when r is equal to 0, that is r raised to 0, this terms become 1. So the first term is 1. In the second term, it would be r is equal to 1, so it would be minus 1. So it is minus 1. And then r raised to power 2, or sorry, n is equal to 2, which is r raised to power 2. That would be minus 1 square, that would be 1, and it would be multiplied by 1, so we get 1. So 1 minus 1, it is a sequence of 1, 0, 1, minus 1, 1, minus 1, 1, minus 1. And similarly, in this case, if you look at it, a is equal to 2 and r is equal to 5. So when you start with 0, so r is equal to 0, you get 2 into r, which is 0, which is 1. So you get start with 2, and then you start keep on multiplying 2 by 5, which is 5 to the 10, and then you multiply this term, which is r, with 5, which is 10 into 5, which is 50, and 50 into 5, which is 250, and then so on so forth. As you can see that this case, the geometric progression is going very fast. It is increasing really fast. And look at this here, if when r is less than 1, which for example in this case it is 1 over 3. In the case when r is less than 1, in that case, and of course greater than 0, in that case the value starts decreasing rapidly. For example, it starts with a 6, and then we multiply it by 1 by 3, it becomes 2, and then it becomes 2 by 3, 2 by 9, 2 by 7, and so it keeps on decreasing and decreasing. So geometric progressions tend to be very fast, and when I say fast, I need to compare it with something relative to what. So what is the to what it is compared? So it can be compared to arithmetic progressions. Arithmetic progression is a sequence of the form a into a plus d, a plus 2d, and a plus nd. So as you can see all these terms, here the initial term is a and the common difference. So we call it a difference, and it is we are adding it. So we're just adding it. D could be negative. In that case, it would be decreasing, and if d is positive, then in that case the arithmetic progression would be increasing. So a is equal to minus 1 and d is equal to 4. So for 0 it would be, so here again please note that the first term is a plus 0 into d, right? So the first term is 0. Here n is equal to 0, so therefore we get a. So if you see the sum sequence becomes minus 1, you start with minus 1, then you add 4, 3, then you add 4, it becomes 7, then you add 4, it becomes 11, and so on so forth. Similarly here you start with 7 and d is negative, so it keeps on decreasing. If you start with 7, 7 minus 3 is 4, 4 minus 3 is 1, 1 minus 3 is minus 2, and so 5. Similarly the last example, here it is positive, so it keeps on increasing. So relative to the arithmetic geometric progression, arithmetic progressions are slower. They change slowly. So here we have a very important definition, which is the definition of a string. A string is a finite sequence of characters which are taken from a finite set, which is called an alphabet. Now the alphabet is represented by sigma in some cases. So in the case of English, it would be ABCD. But when we are talking about bits of characters, this sigma would be 0 or it would be 1. So sequences of characters or bits are important in computer science. For example, if I say my alphabet is 0 and 1, so that means all the strings would be created from this. And if I say I have character string 0, 1, 0, 0, 0, 1, so that would mean that the zeroth element is 0, the zeroth term is 0, the first term is 1, second term is 0, third 3, and it gets the values from the alphabet. And when we want to represent empty string, we can't just say it's an empty string, so we have a symbol for that as well. And then we have a length of the string, which means At 1, 2, 3, 4, 5, 6. So in this case, it is the length or size of the string is 6.